Alright, I have your exams graded and I will turn them back at the end of class. So, there you go. Yeah, just remind me at the end of class because I almost forgot to give it to the last class. So. Alright, questions. So I had said today could be a review, just ask questions, fill in any, try to make sense out of any gaps or anything. Yes?
Did you do 11?
11 on what's in 3.8?
3.8.
Let's see, what did I ask you to do with this? Oh, which book do you have? You have the
International.
Okay.
I think it's the same though.
Oh yes, odd problems are typically the same. Oh, did I ask you to do that one? I didn't think I was going to ask you to do that one. Let's see. We may put this one off a little bit. Well, yes, let's put this one off a little bit. Because I don't necessarily want to worry too much about independent variables. I'm sorry, 3 random variables. Because what we have here, let's just set it up and then figure out what we can do with it. If U1, U2, and U3 are uniform, are all uniform standard, what I call standard uniform random variables on 0 and 1. Then what is the question? If I decide to let U1 be the coefficient, sort of the A coefficient for my quadratic, U2 to be the coefficient for my linear term on my quadratic, and U3 to be my constant term, right? So these are, we're picking random numbers from 0 to 1, 0 to 1, 0 to 1 here. This gives me, right, some expression, and then the question is, find the probability that the roots of the quadratic are real. So it's the probability the roots are real. Okay. So you just plug into your calculator, your little random number generator, and you find the 3 coefficients in that way, and what's the probability that that will actually have real roots? Okay, so how do we just answer that question to begin with? Right, the probability that the roots are real.
The probability that U2 squared minus 4U1 is greater than 0.
Yep, right, because if I have ax squared plus bx plus c, right? And if I want to know the roots of that are going to be negative b plus or minus the square root of b squared minus, did you say a 4 in there?
Yeah.
Maybe you did. 4ac all divided by 2a. And the roots will be real as long as this part is greater than or equal to 0. So in this particular case, as long as u squared minus 4 times u2 squared minus 4 times u1, u3 is greater than or equal to 0, then the roots will be real. Okay. And so what do we have here? Well, we have this big cube. Okay. We have, there it is. Okay. And this is my u1, and that's my u2, and that's my u3. Let's say here's u1 equal to 1, so I would have, here's the point 1, 1, 0 here. I would have, I'd go up to 1 here, and I would have this big cube. I didn't intend to actually, I was thinking about asking this, but I must have typed it in, and maybe, I probably deleted one that I didn't need to delete in all of this. But essentially what I have with U1, U2, and U3, I have something that's going to be a uniform distribution on this region right here. So I have a probability density function, let's just call it little u1, little u2, little u3, which is equal to some constant on the appropriate region, and then it's 0 otherwise. That's what it means to be uniform. And the constant is going to equal whatever the volume of that region is in this particular case, which will end up being 1, or it'll actually just be the, because I'm going to assume independence, it'll be the product of those 3 probability density functions will equal 1. Okay. So essentially, and I'll probably stop it here, although maybe this is where you really want, because I haven't actually didn't work through all of the calculations. I don't want to spend 15 minutes up here trying to figure it out. But essentially what we want to do now is within this cube, we want to figure out the volume corresponding to u2 squared minus 4u1 u3 is greater than equal to 0. So there's a certain part of this cube, looks like some sort of maybe a paraboloid or something that would be sitting sort of inside of it. We want to know essentially our probability will be the volume of the region divided by the volume of the total. And I'll tell you the volume of the total is 1, so what the volume of the region is. So since I did ask it, then I'll write up a solution to this one and send it out to you. But yeah, go ahead.
So since the probability density function is already volume, right? Like it's already 3 dimensions, then it's like the cumulative distribution function in 4 dimensions. So
yeah,
you're looking at like a 4-dimensional volume, right? The probability.
You would be if you had to care about that other dimension.
Right.
So if you are summing together 3 exponential distributions, then the height above each point that would correspond to the x1, x2, x3, right, would give you a 4th dimension, and then you would have to do that type of integral. So here, since every point, that's what it means to be uniform, every point is equally likely, you don't have to worry about that in this case, right? Because you don't have to worry about, because whatever you get, you're going to multiply by a constant, right? It would really be a constant times that region, but it would be the same constant times the volume of that region, and those constants end up canceling out there. Okay. So that's why when we have 2 random variables and they tell us some sort of uniform setting, it means that the probability density function is going to equal to a constant on a certain region, 0 otherwise. That's why we can actually calculate probabilities by figuring out areas divided by areas. Because the extra, I mean, you really, to get the volume that you're looking for, it's a constant times the area, but you'll have the same constant in the denominator, so it'll cancel out. Yeah. I'll write up a solution to this one, but essentially now it's just a question of figuring out what is the region inside of the cube that corresponds to that, and what is the volume of that region. Yeah. I didn't intend to give that to you, so if you don't want to think about it anymore, but I will, since I gave it to you, I'll write up a solution for it. Yes, I wonder which one I did cancel off. I think I took something off of it, and anyway, that's okay. All right, other questions? Yes?
I'm going to joint distributions on part 2.
Part 2, okay.
Yeah. Could we go over number 2, A and E?
Yes. That's, yes. Find, someone have it so I can have one here. Anyway, can I borrow yours for a second?
Oh, I don't actually have one.
I've got one.
Do you have one? All right. Gonna wait out into the. And you accuse of me of breaking the law. All right. So wait, number 2 and number 3.
Number 2, A and E.
2A and B. Okay.
Oh, sorry, A and E.
A and E. Okay.
Sorry.
So in 2, let's see. Consider the joint density function for x and y given. Okay. So we're given this f of x, y equals to 24xy for, there's a couple of ways I could write, but 0 less than or equal to x and y, right? So x and y are between 0 and 1. And additionally, x plus y is between 0 and 1. And then it's 0 otherwise. So for question A, confirm it's a joint PDF, right? Which would mean what?
Would it just mean that it integrates to one?
Yeah.
Okay.
Because it's not obvious that would happen. By the way, on this one, actually on both of these, on number 1 and number 2 out of this one, they are fundamentally different than, there's a difference between those and what I had asked you before. On the last homework, everything was independent, right? So if you look back at the last homework that I had sent out solutions to last Friday, every probability density function, every joint probability density function I gave you off of that was what we would call independent. Because it turns out they're just is that true? Oh, not number 2. Number 2 had the circle. But other than number 2, number 1, number 3, and number 4, they're all independent. Meaning that if you look at them, the probability density functions are just the product of two, the joint probability density functions are just the product of two marginal probability density functions. Now this is not the case for a very particular reason. You can say, well, wait a second, this just looks like an x times a y, because usually when I have this x and y are my two random variables, and if I want to look at the joint PDF, and if I assume independence, right, then the joint probability density function dependent on x and y, under this independence assumption, would just mean it's the marginal probability density function of x times the marginal probability density function of y. And it looks here, right, so if you can write the joint probability density function as some function of x times some function of y over the appropriate region, then that's what happens under independence assumptions. But in this case, it does look like it's an x times a y. So then the question would be, why is this not an independence? Why isn't this the same thing, let me say, over the appropriate region? Why is this not a situation in which I would call it independent? What's that?
Because the 24.
No, 24 is okay. I could break it up as a, a 6 and a 4 or something like that if I wanted to. I mean, is it true that the function is the product of a function of x and a function of y? Is that true? So the problem must be the appropriate region part of it. And what does appropriate region mean? First of all, it has to be rectangular. Right? Because the whole point of this is that you want x not to be dependent on y, and you want y not to be dependent on x. So the functional part of that is that you should just be able to write it as a product multiplication of this one and that one. But if you want x and y not to be dependent on each other, you also need them not to be dependent on each other in terms of the region that you're interested in. And so what we're interested in, we always need to think about the region, we're interested in x and y between 0 and 1, so that would give me a square here, right? X equal to 0, x equal to 1, y equal to 0, y equal to 1, and then x plus y is less than 1. Let's see, here's x plus y is equal to 1 and less than 1, so here's x plus y equal to 1. And what I'm really interested in is that's my region right there. Okay. And so even though this function is a product of two functions that are one's an x and one's a y, there's still going to be a dependence here. It's not independent because the region depends on both x and y, right? That is, if you think about your region here, right, this boundary depends on both x and y. I could write it as y equal to 1 minus x, or I could write it as x equal to 1 minus y. I could write it as x plus y equal to 1, which I already did. And so I can already see that if I know x is large, y has to be small. If I know y is small, I know x has to be, or potentially is going to be large. And once I know something about x, I know something about y. So appropriate region would be rectangular. So if I could do all of this and just say, if for some reason it worked on the rectangle right here, where the boundaries for x do not depend on y, the boundaries of y do not at all depend on x, they're both just constant, that is an additional condition I need for independence. Okay. So if you ever want to come up with a joint random variable that lacks dependence, just give it on a region that that's not rectangular. Okay. And sometimes, like in some of those examples, rectangular means infinitely long rectangles. There are some homework questions that involve 0 to infinity, 0 to 1 or something like that. That's fine. But you just don't want the boundaries to depend on each other. And this line cutting through the middle of here means that those boundaries depend on each other. Okay. So the first question is then, I just wanted to point that out because we are moving into dependence versus independence. The next section that we've already started talking about a little bit deals with independence, and we have certain conditions that need to be satisfied for independence. And of course, when we don't have independence, which we won't always have independence, and actually we don't always want to have independence, because if all of our random variables were always independent of each other, it doesn't matter how much data I gather up, I won't be able to say anything new because there will be no dependence on what I gathered and what I actually want to know. So we like it when things are dependent on each other, right? Because then I could say something about, you could tell me someone's height, and I could tell you something about what I think their weight's going to be. You could tell me something about their education level, and then I could tell you something about what their income is likely to be, right? Right, that's what happens in cases with dependence, right? That's what we want to know is the relationship between things. Okay. So, back to this question. A, I just need to integrate this function over the entire plane, right? And when I integrate everything, right, when I integrate over the entire plane, this function over the entire plane, I should get 1, if it's a real, honest-to-goodness probability density function. Which means in my particular case, or in this particular case, that when I integrate this function 24xy over, that's my r for region, right? Because outside of that region, everything's 0, it's not going to give me any volume, right? That I should get, again, I should get 1. It would have been incorrect to put this put an r squared here because my probability density function is not this, it's this on this region and it's 0 everywhere else. And then I just go ahead and I try to figure out, I'll get this back in a minute. But now I want to go ahead and I need to decide, how do I want to write down that region? Do I want to integrate with respect to x first, or do I want to integrate with respect to y first? Does it seem like it matters? All my functions, everything seems very symmetric, right? It doesn't really matter if I integrate with respect to x. I always integrate with respect to x first, so let's integrate with respect to y first, right? Which means if I fix an x value, right? I fix an x value, some value for x here, then I'm going to integrate over a line like this. So that would look like 24xy, and listen, when I say dy first, it didn't matter. And then dx. And then, let's see, in the y direction, I'll integrate at the bottom y equal to something and the top y equal to something. So at the bottom it's y equal to, and at the top it's y equal to 1 minus x. 0 to 1 minus x. That's what happens in multivariable calculus, right? When we integrate over rectangles, everything's nice and easy because the limits of integration are constant. If it's anything other than that, then of course the limits of integration could depend on the other variables. And then, let's see, we'll finish this thing off. And so then I integrate over these lines, right, from 0 up to 1 minus x. And then I'm going to start over here at x equal to, and integrate up to x equal to what? And then I just have to take it one at a time. Now, sometimes it matters if I did x or y first. Everything here is very symmetric. I mean, even these functions are symmetric. My function up here was a symmetric one. If one of these was an x and the other was like an e to the negative y, then it might matter, because if we do it in the wrong order, we might have an integration by parts or something, which we could handle, but it would just involve more calculations. So you do have to be a little bit careful with such things sometimes. But let's see. X equals 0 to 1. I'm going to pull the 24x out, because those are behaving like a constant when it comes to the y's. And the antiderivative of y is y squared over 2. Okay? And then I'm going to plug in 0, and I'm going to plug in 1 minus x. And I do like to keep track of which variable I'm dealing with, because I need to in some ways, right? I need to keep track of the variable. I want to make sure I plug the right values in for the correct things. And then when I plug in the two endpoints here, I'll get a 1 minus x squared over 2, and then I would get when I plug in x equal to 0, or sorry, y equal to 0, that's a y, I get a 0 squared over 2, which is 0. So it looks like, well, that 2 and that 24 can cancel off to give me a 12. It looks like I would end up with an x, and I would end up with a 1 minus x squared, 1 minus x squared minus a 0, and I'm going to integrate with respect to x. And I don't want to lose my 12, let me just put it outside of the whole thing. And then, oops, I erased my region, but that's okay. So now I need to integrate this. How am I going to integrate x times 1 minus x quantity squared? Probably just going to FOIL it out, right? Probably just want to write it as, so this would be 1 minus 2x plus x squared, and I could write it as x minus 2x squared plus x cubed. And someone tell me if I did that incorrect, but I think that's okay. Dx. And then I would get keep that 12 out in front, x squared over 2 minus 2x cubed over 3 plus x to the 4th over 4, and I'm going to plug in 0 and I'm going to plug in 1. And then when I do that, I get a 1/2 minus plug in a 1, I get a 2/3, plus when I plug in 1, I get a 1/4. When I plug in zeros, I get a bunch of zeros, minus zeros there. And I'm going to guess I get a 1/12 when I do this, so it looks like a 6/12 minus let's see, 2/3 is going to be 8/12 plus 3/12 is 9 minus 8, which is 1/12, right? And then I multiply by 12, and I get 1. So that's what I needed to happen, right? If it's a, so this is 12 times 1/12, which is 1. So if it's a probability density function, when I sum over everything, when I Riemann sum, integrate over everything, I should get 1, and that's what I do get here. So that was A. And then I asked a couple of questions about, so does anyone want to see the marginal density function parts of these? Yes? So let's just go ahead and take care of a couple of them. Because we actually haven't done much for marginal density functions when they weren't independent, and this is a case where we lack independence. So if I want to know, right, so when I take a sample from this random variable, or this pair of random variables, I get these points that are in the, in this rectangle, or sorry, in this triangle, but it's going to take certain values more often than others, right? The curve above this thing will be largest sort of in this region over here. It's going to be highest, and then as I head down this way, and this way it's going to be closer to 0, and over here it's going to be closer to 0, right? So I don't know exactly what it's going to look like over top of all of this. I could pull out mathematics if I really, really, really care, but it's probably going to be something like, you know, something that looks like that, right? Where it's sort of densest up here has the most height, and then as I move off to the sides, then I'm multiplying by things that are close to 0, and here I'm multiplying by 2 things that are close to 0, and so I would get something like that. So with the marginal, let's see, density with respect to x, and we can just do it with respect to one of them because the other ones, everything's symmetric again, would be something like, I want to sum over all of my y values, right? And so I'm going to take my probability density function, my joint probability density function, and I want to integrate with respect to y. I want to sum over all my y's, which in this case means Riemann sum, means the depth, the integral, and I'm going to do that over all the y values, right? Y going from, let's see, fixed x, right? All the y values from negative infinity off to infinity. Well, now I'll go ahead and write down the functions that I'm dealing with, because the function I'm dealing with is 24 xy that I want to integrate with respect to y. And let's see, for a fixed x value, the bottom is going to be y equal to 0, and the top would be y equal to 1 minus x, right? Because this is my y equal to 1 minus x. Right? Actually, it looks like the first calculation that I ended up doing here, correct? Right. Which would be when before I had to integrate the second piece. Looks like what I would get here. So it would be something like 24x y squared over 2, and I'm going to plug in 0 and 1 minus x, and it looks like it'd be 12x times 1 minus x squared, and that would be the marginal probability density function with respect to x. Which is saying that given a fixed x value, and of course this is for, let's be careful about this, what values x does this work for? I'm sorry, yeah, which value x is this true for?
X between 0 and 1.
Yeah, x is between 0 and 1. And so if I know that I have a particular x value, it's going to tell me my probability mass function with respect to that. And remember, the way we can interpret all of this is there is this volume that's above each point in the plane, right? There's a height that's above each point in the plane. If somehow we could just project them all down to the x-axis, right, and take all of that volume and crush it down to, project it down to the x-axis, and accumulate the area there, then that would give me my, it gives me my probability density function with respect to that one variable. And the marginal with respect to y would be doing the same thing if we pushed it all over to the y-axis. Of course, this is all symmetric, so I'll get exactly the same answer for y, f sub y, only with y's in there instead of x's. Okay. So there, that's what you get for the probability density function. The cumulative distribution function, I'll just say anti-differentiate or integrate from 0 up to some point a, where a is a number between 0 and 1. So essentially, it will look a lot like what I would have in one of these cases, but I'll leave it there. E was the last one, or D and E. Okay. So D, with the expected value of x. Okay. So even when I have a joint probability density function, back on question 1, I said, okay, if we're going to deal with something like this, when I have this joint probability density function with respect to two variables, then here's what I'm going to do. I'm going to sum, or integrate, f of xy multiplied by x over the entire plane. Which will mean, in this case, I will integrate over the region that I'm interested in, x times 24xy, right, dA, because that's my probability density function. And then I could go ahead and set up the integral. And I will point out that the only difference between the calculation that we would do over there and the calculation that we would do over here is that I would have an x multiplied by everything, x multiplied by everything. I integrate it with respect to y. That'd be an x squared here, right? It'd be an x squared here. It'd be a squared, a cube, and a, you see, I mean, I'm just carrying along an extra x. This is d, by the way, not e, right? I'm just carrying along an extra x. That would give me a 3 over 3, and a 4 over 4, and a 5 over 5, right? And then I would plug in the 1 and the 0 in the same way. So you should have gotten something like that for that expected value. So essentially, it's the same thing as in the one-dimensional case where you're just going to take the result of the random variable and multiply it by the probability of that thing occurring. And so it's x times this, and then we just have to sum, or in this case, integrate over the appropriate region. And if we wanted to do the same thing for y, we'd do exactly the same thing with a y there. And now e. If I want to do this for x plus y, then I would do exactly the same thing with an x plus y there. So over all the points in the plane, I'll take my x plus y and I'll multiply it by the probability, right? This is the outcome times the probability that outcome occurs, which is what my joint probability density function tells me, and then I would integrate it with respect to it. So the big difference here between E and D and A, right? So A, I just dealt with this. With D, I threw an x in front of there because I want to know the probability of x times the probability density function and then integrate over the region. And for E, I'm just going to plug in x plus y in front of there, and I'm going to go through everything identical in the identical way.
Okay, thank you.
So that was a long way around to get to that answer, but you see all three of them sort of work the same way. And if you remember back with when we first started talking about expected values, I mean the difference, I know when I sum up my probability mass function over all the possible values, I should get 1. And then the expected value will be the thing that when I sum, I'm going to take the outcome and multiply it by the probability mass function. And then that gives me what I call the expected value, right? And so it's the same thing here. We're going to start looking at, what if I have now I have 2 random variables, so I could put an x or a y in there, because I have my joint. But I can put any function of the random variable. So if for some reason I was really interested in knowing the likelihood within a region that I would be a certain distance away from the origin, I could ask, well, what's the expected value of the square root of x squared plus y squared? Right, so I could ask that question, right? Which is really just saying, in this distribution, how far do I expect to be, right, my x from 0, 0 there? And of course that'd be an awful one, right? Because I would be integrating, anytime I have to integrate over the entire plane, and I have this square root of x squared plus y squared multiplied by my probability density function, that's when I'd have to pull up Mathematica or something and have it do the integral for me, because I probably don't want to have to deal with such a thing, right? I already use numerical techniques or something. But I could put any function of x, any function of y. If for some reason I was interested in cosine of xy, right, in here, then the only thing I do is I change this to a cosine of xy, right? That any function of x and y I want to throw in there, I could throw it in down here, but it would only make sense if I could actually make sense out of the integral that came along with it. Okay?
Thank you.
Yep. By the way, with what we know with multivariable calculus, we're going to be able to, when we get to the beginning of chapter 4, see that the expected value of x plus y is just the expected value of x plus the expected value of y all the time, right? Because I know when I start breaking up things like this, I could integrate this with the x here, I could integrate it and I could do all of it with the y there, and then I could add the solutions together and I'll get the exact same answers if I just do it all with the x and y together, right? Which will be helpful, right? That'll be a nice thing to know how to do. Again, I go off the tangent, but that's the idea. Okay, I think that was all the different types of questions on this. Yeah. Right, other questions? Was there any other questions off of this one, or I'll get it back. Thanks. Other questions? Now we can transition into the next stuff, because it's all together, right? We're talking about these calculations that are attached with these joint probability density functions, these joint cumulative distribution functions. And so the next couple of things that we talk about, the next two sections, are independence or lack of independence. And so I'm sort of jumping around these. There's three sections that, well, I'm jumping back and forth between 3.3, which is this idea of just performing calculations like this. And then in the last homework, I gave you a lot of examples that came from independence. By the way, the other class was asking questions off of the homework that I gave solutions to last Wednesday. So they were asking questions on that. This is going to be one of these days because you asked different questions. I'm just going to upload both videos. So if you want to watch the other classes and see what I had to say about that worksheet, you certainly can. And then they did not ask questions like this. And then, of course, I'm going to have to do something with this one because, but I'll get something out to you for that one also. So I'm going to just tell that, I'm going to upload both of those. But let's just go back. On that last homework that I gave out solutions on Friday, every example except for one that I put on there had independence, right? Meaning that the probability mass functions were just the product of the two probability density functions, because they were all continuous cases, the product of two probability density functions on appropriate meaning rectangular regions. And the only example that wasn't of that case was the one where there was a uniform distribution on a circle, right? And that is because, right, the reason wasn't because the functions were dependent on each other. It's because the relationship on the boundaries, there was a relationship between my x's and y's, right? So I had this boundary is x squared plus y squared is equal to 1, or whatever. Whatever the radius was. Maybe it was 3. It doesn't matter. But there's a relationship that, once I tell you information about x, if x is something that's close to 1 or negative 1, you have a really narrow range for possible y values. Whereas if your x is close to 0, you have a wide range of y values. Right? So there's certainly a lack of independence, because as soon as I give you some information about x, you can say something about y in terms of the range of values that could possibly come out of it. Okay? And the same thing for y values. Okay? So in any sort of independence I need a rectangular region, I need those two things I need the x's to not depend on y's and the y's to not depend on x's. So let's see. We can transition over. So that's part of the next section. Actually, the next section we've talked about most of what we need to talk about. This idea of dependence versus independence. I will say that if this is my probability density function, right, under this assumption of independence, it turns out the cumulative distribution functions work exactly the same way. That if I have my CDF here, my joint CDF, if my random variables are independent, then the joint cumulative distribution function will just be the product of the two individual cumulative distribution functions. Again, over the appropriate region. And if I want to compute, any sort of probabilities, the idea is given information about one of them, I get no new information about the other one. So, this is certainly true. Try to make sure, know how I want to make this transition here today. We have situations, let's go back to a discrete case. With a joint distribution. Let's just go ahead and do that. So we saw a case in which our experiment was flip a coin 3 times. And then we decided to have these two random variables, x and y. And let's see, x was the number of heads on first flip, and then y was the total number of heads. And this was the first example we went through when we started talking about joint distributions. And so I had these values x, let's see if I can remember the values that went in there, and my y was a 0, 1, 2, and 3. And I had things like a 1/8 and a 0, and I had things like a, given a 0 and a 1, given a 1 and a 1. This was a 2/8 and a 1/8 and a 1/8 and a 2/8 and a 0 and a 1/8. I think that looks right. And of course, we summed along here to get our probability, our marginal probability mass function with respect to x. So let's double check. Yeah, that adds up to 1/2, and that adds up to 1/2. That's good. And in the y, we get a 1/8, 3/8, 3/8, 1/8. Yeah, that all works good. Okay. And I'll just say, not independent. Right? X and y are not independent. 1/8, 3/8, 3/8, 1/8. And over here I get a 1/2, and I get a 1/2. Okay. And this is my P of x, the next, and here's my P of my marginal probability mass function with respect to some y. Okay. And for instance, how do I know they're not independent in terms of a probability mass function? And I can certainly look at them and I can see they're not going to be, but how do I know they're not? I mean, what does it mean? What does it mean for two events to be independent? Remember? A and B are independent if the probability of A and B occurring is equal to
the probability of A times the probability of B.
Probability of A times the probability of B. And so for x and y to be, and this is true for probability mass functions, so if x and y are independent, then the probability of x is equal to 0 and y is equal to 0 should be the marginal probability x is equal to 0 times the marginal probability, right, well, let me write it this way, probability x is equal to 0 times the probability y is equal to 0. And then that would be the marginal probability of x with a 0 plugged in, and the marginal probability of y with a 0 plugged in. And of course, this is just what we call a joint probability with a 0 and a 0 plugged in. And I can see over here, I get a 1/8. But over here, what is the probability of x, that x is equal to 0? That's 1/2. And what's the probability y is equal to 0? 1/8. And is 1/8 equal to 1/2 times 1/8? No, not equal to each other. Okay, right, and you go through. So essentially, if my two random variables are independent, this is how we can see it in the discrete case. If my two random variables are independent, this number should be the product of these two numbers every single time, right? 0 should be 1/2 times 1/8. 2/8 should be 3/8 times 1/2, right? We can see none of those numbers are the same. Okay? So not only, it doesn't even look a little bit independent here, right? But that's what it's going to mean for those two things to be independent is if the values coming out of my joint probability mass function is just the product of the two marginals, which just means that these numbers, right, all these numbers should multiply to the things in my multiplication table there in the middle. Okay? And that's certainly not happening. We can actually see more. I see most of my probability dependence seems in this area right here. It's something we're going to call a negative correlation. I'm sorry, that's going to be a positive correlation, right? Because when x is small, we get more probability when y is also small. And when y is small, right, large, we get more probability when x is large. That, typically the larger x is, the larger we expect y to be, right? The more likely it is, the more heads we get on the first flip, the more total heads I expect to get. That certainly seems like a reasonable statement there. So if x gets large as y gets large, or vice versa, then and then small and small, I would call that a positive correlation. And we're going to come up with a way of actually quantifying that. Something called correlation. And first thing we're going to have is going to be called a covariance, which is going to be related to something that we already talked about somewhat, which is the variance, right? A variance is how spread out something is with respect to itself, right? With respect to its expected value. Covariance is going to be how spread out two random variables related to each other are going to be, okay? We have a little bit of time before we're going to get to covariance, but we're going to quantify this idea of how dependent two things, or how they might be related to each other, and it's going to involve something called covariance and correlation. But just this idea of independence is nice in the discrete case, because what it means is every time I see these things and I look at the joint probability density function, if they're independent, then these numbers are the product of those numbers, or if those numbers are the product, or these numbers are the product of those numbers, then they're independent. Right? We have, it's an if and only if statement there. And so what we're going to have, and we'll have to stop here, what we're going to have is we're going to have a very similar statement for the continuous random variables, only it's not anything as simple as sums, right? Our sums are integrals because they're Riemann sums. But we'll have a very similar statement that says, well, it basically says this, right? That the density function is just going to be the product of my density functions. And so now to get back, what we're actually going to talk about then on Wednesday is this situation in which we lack independence, because it's going to be nice to try to somehow quantify and understand what's happening when we lack independence. So we'll probably start with this case, and we'll have things like this. Probability mass function, and we'll have a conditional probability mass function of x as it depends on y, and it'll be the question of, can I understand what sort of values x will take given y is taking some particular types of values. Okay. So we can start with, we'll actually just start with this example and finish it off and say, okay, the conditional probability mass function is going to look like, so given a certain value I, what can I expect out of my values of x? Okay. And this will be interesting for us because it'll let us compute probabilities and probability density functions and joint probability density function in this situation of more complicated experiments where something happens and then something happens beyond that, and I want to understand what the total sort of probability density function might look like when I put those two experiments together. Much like we did with Bayes' theorem back, and its related things back in calculus. Okay? So, we'll just be bouncing back and forth between this idea of dependence and independence here. Oh, and see, you're supposed to remind me to give you your exams back, because when I talk, I don't stop.